In this video, we are going to conduct material balance on one system unit and two system unit. And by using the flowchart, labeling and degrees of freedom, we will be able to completely solve the system, as you can see. A liquid mixture containing 45% benzene, B, and 55% toluene. Highlight the important things. By mass is fed to a distillation column. The first thing immediately is drawing the flowchart. A product stream leaving the top of the column. And as we agreed before, we will see the problem statement saying overhead product. Contains 0.95 mole B, 95% is 0.95, and a bottom benzene product. We will draw another stream that will leave the distillation. Contains 8% of the benzene fed to the column, which means whatever is entered here in terms of benzene flow rate, 8% of it will be the flow rate that will leave the bottom stream. The volumetric flow rate of the feed here is 2000 liter per hour. It's a total flow rate. And the specific gravity as well of the feed mixture is 0.872. Now we come to the important thing. Determine the mass flow rate of the overhead, we label it M1, and the mass flow rate and compositions, mass fractions of the bottom stream. So it means we have another stream we want to calculate, which is the mass flow rate of the bottom stream. Not only this, also the mass fractions, which are X benzene, and to minimize the number of unknown information, we will make it 1 minus XB, which is the same as X of toluene. The reason I'm writing X because when you discuss mass fraction, then you say X, and then when you discuss mole fraction, you will say Y. Like here, this one will be Y of benzene. And the balance, as we know, if you have two components, then they must equal to 1, right? 0.05 toluene. We draw the flowchart. We labeled every single information. Don't forget this one as well. 8% benzene fed to column. If you label and if you draw the flowchart, what will be the next thing to do? Degrees of freedom analysis. That tells us, are we wasting our time or not? Number of unknown minus number of independent equations. We have here 1, which is the mass flow rate unknown, 2, and then 3, which is the XB. Don't count this one because when you find the mass fraction of benzene, immediately you will find the mass fraction of toluene. Minus number of independent equation, immediately it will be 2 for a physical system, non-reactive system. It will be equal to 1. One more information we need to solve the system. 8% of the benzene fed here will equal to the mass flow rate of the benzene here in the bottom, which will make it 1 minus 1, and then it will be 0. So we can solve the system. We will not waste our time. And as for the selection of the bases, the moment you are given a certain flow rate of any kind of stream, then you use this stream or this flow rate as your basis. Basis will be the 2000 liter per hour of the feed. And as I said before in the previous video, I think the previous or the second previous video, when you have a volumetric flow rate, then you need to convert it immediately to either mass or mole flow rate. Because we do have mass balance, we do have mole balance, but we don't have volume balance. But the question, which one do we use? Mass or mole? Because here we have the mass fraction, we have the mole fraction. Still, with degrees of freedom analysis, you will not waste your time. You know that it is a solvable unit, but how lengthy is the calculation that I'm going to do? So we need to analyze the situation here. We have been asked to find the mass fraction and the mass flow rate of the top and of the bottom stream. If it asks about finding the mass, it makes sense that we need to convert this one, this volume flow rate, into mass to ease the calculation and make our time less shorter. If you do so, then you say, you know that rho times V is equal to mass flow rate. We know that rho, you can find it using the specific gravity of the mixture multiplied by the reference density, which will be water. So if you say 0.872 times 1000, this will be the density, and then multiplied by the volumetric flow rate, which will be 2000. This will give me the mass flow rate. But the problem here, we have this one meter cube, but this one liter. So we need to convert one of them to the other to cancel one of them from the other. Convert this 1 liter. And I know that 1000 liter is equivalent to 1 meter cube. To cancel liter with liter, and here meter cube with meter cube, I will end up having kilogram per hour, which is what I want. If you do so and if you calculate it, you will find that the mass flow rate of the total stream, the feed stream, will be 1744 kilogram per hour. The second thing is to utilize that whatever benzene flow rate enters in the feed, 8% of it will leave in the bottom stream. Mathematically, it will be 1744 times the mass fraction of benzene, 0.45. This is the flow rate of benzene. 8% of it, or 0.08, they are the same, will be the mass flow rate of the benzene leaving, which will be the total mass flow rate multiplied by the mass fraction of benzene. M2 times XP is the mass flow rate of benzene in the bottom stream. And 8% of it will be the flow rate of the benzene leaving at the bottom. And the answer will be 62.8 kilogram per hour. We can write this one, as I said before, as M2 benzene. It is the same. Notice now that you know the value of the benzene in each stream. That's why if you want to find any unknown now, it will make sense that you should start from benzene. That's why we will do now benzene balance. Take the benzene flow here, 0.45 times 1744. And if you have a steady state non-reactive system, then it must equal to M1, which is the overhead product, times the mass fraction of benzene. Add to it mass flow rate of the second stream times the mass fraction of benzene, or as we agreed, we will write it as M2B. Why is that? Did we change the subject here? No, we didn't change it. But because we know the value of M2B, that's why we'll write it. Be careful now. Don't use the 0.95. And it happened to me in the exam. I used the mole fraction inserted in the calculation, and the scale was in mass. And I didn't get the grade, even though I solved all the question. Because I was in a rush and I didn't know these very important stuff. Flowchart, labeling, degrees of freedom analysis. But now we do know that we have a mole fraction here, 0.95. And so we must convert the mole fraction into mass fraction. And here is a certain quite nice rule. If you are converting mole to mass fraction, then choose always to simplify the calculation. You can use any basis, even your name. You can use your name as a basis. But to simplify the calculation, choose your basis as 1 mole. It will be very simple and you will find the fractions fast. The component, benzene, toluene, mole. If you say 1 mole, then you know that the mole fraction, it's given already, 0.95, 0.05. If you multiply 0.95 by 1 mole, you will find the mole of benzene, which will be the same, 0.95. You see, it will be simple if you choose 1 mole. But if you choose 100 mole, then you will say 100 times 0.95. It will be 95. The same thing, you will say 1 times 0.05, which will be 0.05. This is the mole amount. Now, you will use the molecular weight of each one of them. Benzene molecular weight is 78.11. Molecular weight of toluene is 92.13. Refer to table B1. If you are using Elementary Principles of Chemical Processes book, you will see the molecular weight of each single component. After the molecular weight comes the reason of saying 1 mole. When you convert from mole to mass fraction, you will multiply this one by 78. And if you choose a basis of 100, then you will say 95 times 78.11, which will be very, very large. That's why you use a very small base to simplify the calculation. And then you will say 0.95 times 78.11. This will be the mass. A value of mole times a value of gram per mole. So you will cancel mole with mole and you will end up having gram, which you want, 74.2. And here the same thing. You will say 0.05 times 92.13, which will be 4.61. And now if you want to find the mass fraction, which is X, the mass of the benzene divided by the total mass, which will be in this case 74.2 plus 4.61. And the answer will be 0.942. This is the mass fraction of benzene in the overhead stream. And the remaining will be 0.058. You see this mass fraction, 0.942, it will be this one. And now you have every single information in this benzene balance. The only thing you don't have is the mass flow rate of the overhead, which you can find easily. We know M2B, 62.8 kilogram per hour, and the answer will be 766.45 kilogram per hour. The mass flow rate of the overhead. And now take a quick scan on the flow chart. You will notice that you have the mass flow rate of the feed, the mass flow rate that you just found, which is the overhead, but you don't have this one. So the simplest thing to do is just a simple math problem, total balance. You see 1 plus 1 is equal to 2. This is the same thing that we will do now. 1744 is equal to 766.45 plus M2 that we want to find. If you solve for M2, the answer will be 977.1 2 kilogram per hour. The fifth step is to ask you a question, my chemical engineering friend. Would you do benzene balance again to find the mass fraction of benzene? Or as a faster way, you take this benzene and then you divide it by the total mass flow rate, which is 977.12. If I took mass amount and then I divide it by the total mass, it will give me the mass fraction, right? So if I do this, is like I'm saying M2 benzene divided by M2 total, and this is just the mass fraction of benzene. Faster way, and the answer will be 0.0643. And you know the famous equation now that we are glad it exists. If you add mass or mole fraction of two components, then the answer will always be 1. We have the mass fraction of benzene, then 1 minus 0.0643, then it will equal definitely to the mass fraction of toluene, which will be 0.9, about 0.963. So we did a lot of stuff here that makes our calculation short. To summarize everything, we converted this 2000 liter per hour into mass flow rate because I don't want to trouble myself. It asks me to find the mass fraction and the mass flow rate, so it makes sense that I convert this into mass flow rate. And then when I convert mole fraction to mass fraction, I use a very simple basis. This is the second thing we did to ease our calculation. The third thing is to ask ourselves, we did find the mass flow rate of benzene in this stream and the total mass flow rate in this stream, so it's easier to divide to find the mass fraction and then the remaining, which will be toluene. Engineering is not just solving, it's just about recognizing what you have, what you are asked to do, and then to quickly find the solution faster. If you do another solution, then it will be also fine, but this is the shorter version. I lectured you about engineering, but when you consider two system unit, then you will actually need this skill because you don't know where to conduct your degrees of freedom analysis. 4500 kilograms per hour of a solution. Plus, I should mention something. The question always will try to trick you in the fancy English language. Like here, it wrote 4500 kilograms, which is 4500 kilograms. Then when it says per hour, that's simple. 4500 is 4500 of a solution, and as we agreed before, when we have a solution, then it means that there is water. There is 1/3 K2CrO4, which is potassium chromate. We will label it as K, and it is by mass. We are talking about mass fraction. Is joined. This is another keyword. It will not say enter, it will not say come, it will say joined, and it will trick you. It means enter, mixed by a recycle stream. And as we agreed before, recycle means it will go back somehow. From where? We will see. Containing 36.4% K. Then the remaining will be water. And the combined stream mixed together is fed. Fed here enters the evaporator. Let's start drawing to make it clear. 1/3 K2CrO4. The remaining will be water, which is 0.667 H2O. Will enter by a recycle stream. So there will be somehow a recycle now joining this feed. 36.4 is fed into an evaporator. This will be the evaporator, and once it said evaporator, it means there will be some water leaving, pure water. This concentrated stream will contain 49.4% K, which means 0.494 K, is fed into a crystallizer in which it is cooled and filtered. This implies that we should write a certain block responsible for crystallization and filtration. The filter cake. What is filter cake? It is the product. It is composed or consisted of two things. One is the K crystals, and the other will be a solution that contains 36.4 K. Also 36.4 talks about this one, is the recycle stream. We will take a split of this one and we will make it recycled to join the fresh feed to the evaporator. And now if we label everything, call this M1 with XK and XH2O, because once they are mixed, you don't know the value. We have here M2 and then M3. This filter cake composed of mass, we call it M4, and this M4 is pure crystal, pure potassium chromate. But the recycled one, we will label it as mass flow rate of the 6th stream. This one we will label it as the 5th mass flow rate. The composition here will be equal to the composition here because this is a split point. Now we labeled everything. You don't have to label anything here, M2, because it's pure water, which means that the mass fraction of the potassium chromate will be 0. Find the evaporation rate. This is M2. Find the crystalline production rate, which is M4. The feed rates handled by the evaporator and the crystallizer. We are talking about M1 and M3. And then the recycle ratio. It's recycle mass divided by fresh feed mass. It's M6 divided by fresh feed. It's not this one. It's not this one. We are talking about fresh feed. This one. 4500. Once you know M6, we will find the recycle ratio. But to find M6, there will be a long story. This is exactly what I mean by a tricky situation. You have more than one unit, so you don't know where to start your degrees of freedom analysis. Yes, in the senior design, we solved the problem, but I introduced the problem 1 unit by 1 unit. But now we have 2 units. So the selection of the balance you will do will be different. You could do balance here, overall balance. The one that enters the fresh feed and what leaves overall system. You could do balance around the evaporator itself. You could do balance around the crystallizer itself. You could do balance around these 2 units, what enters the first unit and what leaves the second unit. The one that you will choose is the one that will give you degrees of freedom analysis 0. If you do overall boundary, what comes is 4500 and what leaves the unknowns will be M2, M4 and M5. So you'll have 3 unknowns and we have water and we have potassium chromate, so we have 2 independent equations we can write, which is greater than 0. But it is given the crystals, which is this one, M4, account for 95% of the total mass of the filter cake. The total mass of the filter cake is M4 plus M5. 95% of M4 plus M5 will give you M4. That's the meaning. So we have an information in the product stream that will leave the overall boundary. 1 minus 1, it will be 0. It tells you that you can start from the overall boundary. You might ask, why did you immediately go and then you did the overall boundary and then conveniently it is 0 degrees of freedom? I started with the one that I know. You know this information, so you kind of expect that it will give you degrees of freedom 0 or at least close to 0. We will not be able to solve if you take balance around the evaporator and the crystallizer. M1, XK, 2 unknowns, M2, 3 unknowns, and M4, which is 4 unknown. And then you have the information, okay, minus 1, and then you have 2 independent equations, okay, it will be 1 degrees of freedom. Around the evaporator, M1, XK, M2, M3, you have 4 unknowns, 2 independent equations, you have 2 degrees of freedom. You cannot solve the system. If you do balance around the crystallizer, then you will say M3, you don't have it, M4, you don't have it, M5 and M6, you don't have 4 flow rates. You have 2 independent equations, you will have only 2 degrees of freedom with the information. You will have only 1 degrees of freedom, which is why we will start with the overall boundary. And if you do overall balance on the overall boundary, the unknowns are M2, M5 and M4. Now we will use the information because it doesn't make sense. You have 1 equation with 3 unknowns. M4 is equal to 0.95 times M4 plus M5. Solve for M4, it will be equal to 19 M5. We will substitute here 19 M5. 4500 will equal to M2 plus 19 M5 plus M5, it will be 20 M5. Still, you don't have the M2 here. Maybe overall balance will not do. Try another thing. Definitely you know that this system or this boundary is solvable because the degrees of freedom is 0. If it is not overall balance, then it means that there is another balance that will solve the unit. So let's try to do potassium chromate balance. If you do that in the overall boundary, 0.333 times 4500 to give you the mass flow rate of the K will equal M4 pure potassium chromate plus 0.364 times M5. You will notice that I didn't write M2. The reason is because M2 is pure water. And now use the information M4 equal to 19 M5. We only have M5 unknown. M5 will equal to 77.4. Immediately you find this, then M4 will be 1470.3 kilogram per hour. You did find M4, you did find M5. What will you do is the overall balance. Go back to it. If you solve for M2, the answer will be 2952.3 kilogram per hour. Now we will use crystallizer and filter boundary, you have M3 and you have M6 unknown. M4 and M5 we found them before. So two unknowns, two independent equation, the answer will be degrees of freedom 0. H2O balance because we want to get rid of M4. And if you do total balance, then we say M3 equal to M4 plus M5. We do have M5, we do have M4, and we do have here M5. In each equation you don't have M3 and M6. You have two equations and you have two unknowns. Solving simultaneously, if you calculate it, will be approximately 7191. Solving for M6 will yield about 5643.3. M2, M4, M6. Recycle ratio is 5643 divided by 4500, and the answer is about 1.254. It's dimensionless, it is unitless, the recycle ratio. We just need to find now the feed rates. You can simply do evaporator, but of course there is a way here. Here, the mixing point, a simple total balance problem. M1 will be 10,143 kilogram per hour. And this concludes the question. We also found M1.